All right, section 6.5. Today we're going to evaluate definite integrals. So the idea here is we're going to be working on the FTC like we did last time and kind of add on to that with a couple of new concepts. And we're also going to be applying the FTC to problems where we're going to be using substitution with our integration. So we're going to apply properties of definite integrals, which I'm going to show you, pretty cool properties. We're going to use integration by substitution to evaluate the definite integrals. I'm going to show you two methods. I'm going to tell you which one I prefer, but you can decide. We're going to find and interpret average value of a function on a closed interval. So a lot of stuff to do today, but all really, really good stuff and extremely important. So let's get into it. The first thing we need to talk about is properties of definite integrals. So we introduced definite integrals last time. Now we need to talk about how to work with them. Imagine, for instance, that you're trying to integrate over the region from A to A. This is your first property. That integral is 0. So if your upper and lower limit of integration are the same value, then you're not covering any area. So the area under that curve would be 0. This is, don't ask me why. I don't know. Why is this my favorite property? I don't know. It's so useful, I think, that especially if you end up going on to take up to, I use this property all the time. So this one, it might not look that weird to you, but it's talking about the integral from B to A of f of x dx. Wait a second, isn't it the integral from A to B? I mean, it doesn't, you can still take the integral from B to A, but a lot of times we like to go from left to right. So to write this property, you can switch the upper and lower limits of integration and then make the integral negative. So this is a cool property. You might never, ever use it in your whole life except for today. And if that's the case, I'm really sad for you because it's a really cool property. I don't know why. I don't know why something so simple as this is like really exciting to me, but I really love this property. I find it super useful. I use it all the time. So you can switch the upper and lower limits of integration if you make the integral negative. Another one is the sum of two integrals. So this is kind of this idea where, like, let's say I'm going from A to C, and I'm integrating over this curve. So if for whatever reason you don't want to go all the way from A to C, like let's say you cut this off somewhere in the middle, I don't know, maybe you had some reason to stop at B, you can take the integral from A to B and then add that to the region from B to C and end up getting the same quantity. So whether you go all the way from A to C or go from A to B and then from B to C, you're still going to be covering the same amount of area. So that's what this property is saying. It's just saying that you can split up the integral from A to C by picking some value in the middle. So it'll be upper limit for one integral and your lower limit for the other, but this will just cover that whole region. You may or may not use this very much in this class, but it is a property at your disposal. Then we have the integral from A to B of f of x plus g of x. So this is sort of just that sum or difference property that we're going to be using. It's just saying that you can take the integral from A to B of f of x dx and then take plus or minus the integral from A to B of g of x dx separately. So whether you add or subtract inside the integral or whether you make two separate integrals and then add and subtract, this property is just saying you could do it either way. I think that's a little more intuitive for students, but this is formally giving it to you as a property for definite integrals. Last but not least, we have your constant multiple property, which is saying if you multiply by a constant multiple inside the integral, you can pull that constant multiple out of the integral and just integrate and then multiply by a constant. So we've used this before in this class. So it is a property that you can use. All right, so now we're going to use these properties in the next example. I'm giving you two integrals. Now, the nice thing about this is I'm not telling you the definitions of the function. Expect to see something like this on your test. I'm just giving you some information about the integral, and then you have to use properties to actually answer the question. So since I haven't given you a function, you can't actually use the FTC to evaluate anything. You have to use properties. I love these. Okay. I'm giving you these two pieces of information, and I'm asking you to now find the integral from 10 to 3 of f of x dx. So there are a couple different ways of doing this. One of the first things you might notice is the lower limit of integration is actually a larger value. And if you're thinking that that's odd, especially since you have an integral here that shows up with the lower limit of 3 and an upper limit of 10, you might want to rewrite this. So the way I'm going to do this using my favorite property that we don't know why is my favorite property, but it is we're going to make this the negative integral from 3 to 10, just switching limits of integration. I forgot my dx there. Oh. All right, so it looks like that. All right, now that we have this, we can use our other property that says that I can chop this off somewhere in the middle. That's essentially what's being done here, is you have an integral that went from 3 to 7 and then from 7 to 10. As long as you're covering that whole space from 3 to 10 and you're not missing anything, then we can just write this as the integral from 3 to 10. So that's because these two are the same, 7 and 7. If this first 7 was a 6, we wouldn't be able to write it like this because we'd be missing that space between 6 and 7. But in this case, we can go ahead and write it as the negative. Don't forget, when it's a negative, you must include parentheses or brackets because it has to get distributed. But it's negative, and then the integral from 3 to 7 of f of x dx plus the integral from 7 to 10 of f of x dx. Okay, so we're taking the negative of that sum. Now, I've given you both of these values. The integral from 3 to 7 is 8. The integral from 7 to 10 is 5. Add them up and you get 13. Apply the negative and you get negative 13. So this is just a question of, like, you know what the properties mean and can you use them? That's it. Nothing too complicated. Use the properties. So that's how the properties work. Now, on to the meat and potatoes of this lecture. We are going to talk about how to use substitution with definite integrals. So if you're thinking, like, didn't we already do this? We did not. We talked about how to use integration by substitution in 6.2. And then in 6.4, we talked about how to use the FTC, the fundamental theorem of calculus, to evaluate definite integrals. And they were the type of integrals that we saw in 6.1. So it was a good review of 6.1. But now we're going to apply the FTC to integrals that require substitution from section 6.2. So we're gonna, everything is just kind of coming together here. Here's the idea. We have two different methods. Now, I have a method that I prefer, but I know it's not the method students prefer. I'm going to show you both. And I sometimes don't like showing you both because sometimes students try to mix up the methods. They do both methods at once and then everything's wrong. I'm going to try to show you some pitfalls, make sure that we all know what we're supposed to be doing. But I'm showing you both methods because I do want you to be able to use both whenever you need to. Okay, so the first one would be you integrate with respect to u, you go back and back substitute for x, and then you use your original x limits when you're applying the FTC. The other method, keep your integral in terms of u and rewrite your limits to also be in terms of u. Now, the second method is my preferred one. This one's my favorite. And then this first one is the one that students tend to like. I don't know why. I just feel like they think like this is the most straightforward. You decide. I'm not going to force you to use one method or the other. The reason I really like the second one is because I remember being in college, and my calc teachers in Calc 2, Calc 3, or anytime I ever had to use calc again after I learned integration by substitution, they always switched their limits. So I was very resistant at first, and once I realized, like, I better figure this out because this is what everybody's doing, my life became a lot easier. So stop resisting. Now, that being said, I'm going to give you your first example. This is the integral from 0 to 1 of x over 5 plus 2x squared dx. So this is a substitution problem. If you don't recognize that, I mean, think about what else you could possibly do to integrate this right now. You can't split up the denominators because you only have one term in the numerator. There's really no other way that you could write this. Another thing you want to notice for substitution is remember that you want the derivative of u to be sitting inside the integral. Well, we also said that if you have some sort of function that isn't clearly a composite function, usually we try to let the denominator be u. Well, that's going to work out for us in this case. So if we let the denominator be u, we'll be able to see that its derivative is actually already sitting in the function. So let's let the denominator be u, which is 5 plus 2x squared. And then du is 4x dx. Now, I don't have 4x dx. That's fine. I have just x. So go ahead and divide out that 4 on both sides, and then you'll get x dx. Okay, so I'm going to first show you the method of back substituting using the original limit. So when I do that, I'm going to keep the original x limits on the integral. So I'm going to rewrite everything else in terms of u. And I try to be very particular here about making sure I label limits of integration so that it's very clear that they are corresponding to the variable x. Okay, so I'm going to rewrite my function. I'm going from x equals 0 to x equals 1. That's what this means because I'm integrating with respect to x. My limits are given to me with respect to the variable x. So I'm going to leave the original x limits on here. But x dx is getting replaced with 1/4 du. And then in the denominator, we already made the denominator equal to u. So I'm just dividing by u in this case. I'm going to rewrite this one more time. 1/4 times the integral from x equals 0 to x equals 1 of 1 over u du. I know that students don't like to write additional stuff if they don't have to, but I think this is really going to help you to keep track of what you're looking at. So I would really strongly suggest writing these limits of integration with an x equals. Okay, so now we can say this is 1/4 times the natural log of the absolute value of u. Don't forget those absolute value bars. And then this is going to be getting evaluated from x equals 0 to x equals 1. Well, at this point, you should be looking at this and thinking like, oh, yes, I'm looking at this for x, not for u. So you're going to go back and match your variable in your completed integrand or your integral with these limits of integration. So I'm going to back substitute for x. So instead of saying I have 1/4 ln u, I'm going to say I have 1/4 times the natural log of, and then because u can't possibly be negative, 2x squared can only be positive, and then you're adding something to it, I'm going to drop the absolute value bars and just put parentheses around this. Just because the absolute value bars are redundant. But of course, if you want to include them, it's not going to hurt anything. Now when I evaluate this from 0 to 1, I'm looking at the same variable. So I can actually evaluate this now. So I have 1/4 times natural log of 5 plus 2 times 1 squared. And then minus the natural log of 5 plus 0. And then we'll just simplify. So now I can say this is, give me some space here, 1/4 times the natural log of 1 squared is 1 times 2 is 2 plus 5 is 7. And then minus, I should put my parenthesis here, the natural log of 5. Now, I'm not going to be super picky about this, but if you have the natural log of 7 minus the natural log of 5, you really should write this as the natural log of 7/5. Remember using that quotient rule for logarithms? It just looks a lot better, in my opinion. So I would write it like this. Okay, so that's method 1. So this is the method of back substituting. The next method that I'm going to show you, we're going to do the same integral, but this time we're going to do it using using the method of changing our limit of integration. So other method, we're going to change our x limits to u limits. That's what we're going to do now. So same problem. I'm going to start it out the same way. We're going from 0 to 1 of x over 5 plus 2x squared dx. Now, it's the same idea as what we did before. We said, okay, we're going to let u be the denominator. Then du is 4x dx, and 1/4 du is x dx. When you change your x limits to u limits, I recommend doing the whole substitution all at once, because I think if you start to plug in half of it and then you start to rewrite, then you almost get confused. Like, wait, what am I still missing? What do I need to do? And then it gets jumbled. So if you're going to change everything over to u, do it all at the same time. I feel a sneeze coming up. Okay. All right. All right. So what I'm going to do now is right now I have an x equals 0 and an x equals 1. So we kind of talked about that previously as these are x values. So I'm going to list these out, and I like to list them in the order in which I see them. So x equals 1 is the top limit and x equals 0 is the bottom. What I need to do is rewrite these in terms of u. So you already just said that u is 5 plus 2x squared. So if I want to change x equals 1 over to a u definition, I'm going to say that u is 5 plus 2 times 1 squared, which is 7. And I'm going to do the same thing for x equals 0. U is 5 plus 2 times 0 squared, which is 5. Now, if you've already done this the other way, these numbers should look really familiar to you. These are the same 5 and 7 that came out of your first integral. But what you're going to see now is we're going to use them directly in the integral, and we're not going to back substitute. So now I have new u limits that I'm going to put on the integral when I write everything in terms of u. So we have x being 1/4 du. Why? Oh, never mind. I swear I do have whiteout. I swear I do. It's perhaps, here we go. Oh, guys, just like, I don't know what it is with me forgetting the whiteout. All right, I have it. 1/4 du is x dx. U is the denominator. So I have 1 over u du. And now instead of putting x limits on this like I did previously, I'm going to switch it over to my u limits, and I'm going to have the whole integral written in terms of u. So this is going to, instead of saying x equals 0 to x equals 1, I'm going to say this is going from u equals 5 to u equals 7. Now, as long as I have the entire integral written in terms of the same variable, I don't want to back substitute, because right now everything's in terms of u. I can use the FTC with this integral, and it means that I should not back substitute because I already found u limits. So the key here is do not back substitute. We're going to use the FTC on the integral as we see it. So I'm going to integrate 1/4 times the natural log of the absolute value of u. And now I can take this directly from u equals 5 to u equals 7. And I don't back substitute because I have the same variable showing up in my limits of integration. This is why it's it's just a smoother process to go through. So I have ln 7 minus ln 5. And of course, these two are positive quantities. I can drop those absolute value bars. And then I arrive at the exact same conclusion where I have 1/4 times the natural log of 7/5. So personally, I find this method of changing x limits to u limits just to be the smoothest way of finding these definite integrals, because now I don't have to back substitute. There's nothing messy about it. I make one big substitution. I change everything all at the same time, and then I just use the FTC. So this is the method that you're going to see me use the most often. If you want to use the method of back substituting, that's fine. But I'm going to tell you the problem here. What I see with students back substituting is sometimes they change their limits of integration and they also back substitute. I've seen so many students do this where they do both things. You cannot do both. You have to pick one. You either back substitute or you change your limits of integration. You don't do both. It's, you know, this is such a big deal. I'm even going to write a note out of it. So you're either going to back substitute or change the limits of integration. Never both. Okay, so you back substitute at the end, evaluate with your x limits, or you change your limits of integration from the beginning and use the FTC. You're not going to do both things. Repeat that after me. I am not going to do both of those things. I am not going to do both of those things. I'm only going to choose one. I don't care which one you choose. Just don't do both. Because then the answer will be wrong. Even though you did a lot of work, it wasn't the right work. Is that your mantra? Are you repeating after? I'm not going to do both of those things. I'm going to back substitute, or I'm going to change my x limits to u limits. I will not do both. I'm giving you all a look. Giving you the look. Number 2. Number 2. This is the integral from 0 to 2 of 3x squared e to the 2x cubed dx. Now, I hope that you're looking at this and you feel like, all right, this is clearly a substitution. First off, if the inside function is the exponent, you're looking at this function x squared as being 1 degree less than x cubed. So right there, you have a derivative. So in general, when you have some sort of integrand with e to a function of x, the exponent is going to be your u. And, you know, sometimes we don't know, we just have to try stuff. And maybe we're wrong, but that's okay. That's the process of integration. You're a lot of times going to try the wrong thing before you find the right thing. That's okay. That's how we learn. U is 2x cubed. Du is 6x squared dx. I don't have 6x squared dx. I can create a 3x squared dx if I want to do that. Or you can pull the 3 out and just create an x squared dx. I think this time let's go ahead and create a 3x squared. If I want to turn this into 3x squared, I can divide both sides by 2. I can multiply both sides by a half. So I can do 1/2 du is 3x squared dx. That's just because I multiply both sides by 1/2. Multiply both sides by 1/2. So now I have 3x squared dx. This is my 1/2 du. And then I have e to the u as the other factor inside the integral. All right, I'm going to start out changing my limits of integration to u limits because I like to do that. And I think it's very sophisticated. So I like to do the thing that's sophisticated. I have x going from 0 to 2. 0 to 2. And what I need to do is get this rewritten in terms of u. Well, u, we said, was 2x cubed. So I'm going to take my u, which is the 2x cubed, and I'm going to rewrite my limits of integration using that quantity. So that means that u is 2 times whatever x is cubed. And I'm going to do the same thing for 0. Okay, so anywhere you see x, swap out or substitute it into this expression. And then you'll get u equals 16 and u equals 0. These are the new limits of integration. And that means that we're not going to back substitute when we're done. We're just going to apply the FTC when we rewrite our integral. This is awesome. Let's go ahead and rewrite it. So we already said that 1/2 du was 3x squared dx. So I'm going to write the 1/2 out front. The du can go inside the integral, and then I have e to the u inside the integral. So this is 1/2 times the integral of e to the u du, and now I'm going to put those u limits in there. If they're all in the same variable, I'm not too concerned about putting a u equals, but it couldn't hurt. So if it could possibly help, which it could, put them on there. U goes from 0 to 16. Okay, so this is that method where we're changing the limit of integration. So I'm just going to go ahead and integrate and then apply the FTC. I don't back substitute here. So I have 1/2 e to the u going from u equals 0 to u equals 16. And then I'll evaluate. So this is going to be 1/2 times e to the 16 minus e to 0. E to the 0 is 1. So this is just going to be 1/2 times e to the 16 minus 1. No back substituting required. Now, let's say that you were like, oh, I should change my limits of integration, but I forgot to do it. Or like, I forgot how to do it. And that's okay. You could have done this with the other method. The way that you would have done that is you would have written your substitution exactly the same way, except you would have left the original x limits on there. And now when you see an integral that has 2 different variables in it, that should be ringing alarm bells in your head. Like, wait, I can't have 2 different variables. At some point, I'm going to have to switch back. I got to get everything uniform. So this integral is 1/2 e to the u, and then you're going to evaluate that from x equals 0 to x equals 2. And now you're thinking like, okay, I got to back substitute. Your original u was 2x cubed. So you would go back in here and say 1/2 times e to the 2x cubed, and then you'll go from 0 to 2. And you'll end up getting that same quantity of e to the 16th minus e to the 0, which is 1. So you'll get the same answer. It's just a little bit of a different process. Like I said, I think it's messier. Anytime I can avoid having 2 different variables in the same integral, I avoid it. But listen, I can't make you do it. I can't make you. You know, let me tell you, the reason I was so bad at this as a student was either because I wasn't paying very close attention when my teacher taught it, or it's very possible that when my teacher taught this to me, they just maybe didn't teach it very well and I didn't pick it up. Like I was confused. Like, wait, what am I supposed to be doing again? Or maybe I was sick that day. I don't know. I'm trying to make a really big deal out of this, and I'm trying to teach this as well as I possibly can, because I don't want you to resist it the way that I did. Because eventually I had to get on board and change my consideration. So I really want you to just get into this habit where you just do this and it's not a big deal. Okay. This is my wish for you. Okay. Let's do another one. Number 3, we're going to go from 1 to 5. It's x times the square root of x minus 1 dx. Okay. I really like this problem. I don't think we did anything like this in 6.2, but it's a great integral to go over. The technique is slightly different, just because you have x to the first power in both cases. So if you're looking at this and you're like, wait, I don't see a derivative sitting outside of here, we're going to have to force it, and that's okay. So if you're thinking, okay, this is a composite function, I'm going to let u be the inside function. That's a great place to start. We're going to say that u is x minus 1, which is your radicand. So that means du is dx. Well, what about this extra x that's sitting here? We need to account for this x. We need to rewrite this in terms of u. And it did not pop out in our substitution. When we substituted, basically all we got was that we're taking the square root of u, and then dx was du. But we couldn't cover the x. We had nothing to substitute for it. It's still sitting there. So that's not good. I mean, it's not terrible, but we're gonna substitute it out. And the way that we're gonna do that is we're gonna again use the expression that we already have for u. This is the base for everything we're doing in this problem, or any substitution problem. If I know that u equals x plus 1, well, then I can rewrite this for an x equals, and I can say that x equals u plus 1. It's the same thing, right? They're saying the same thing. Add 1 to both sides, and you get x equals u plus 1. Well, now I can rewrite my x, this one, as u plus 1. Everything's covered now. Or is it? I was thinking everything's covered inside the integral, but what about limits of integration? We should definitely talk about those. There's a lot going on here, but lots of little things. I want to switch my limits over to u limits. So x is going from 1 to 5. And I know that u equals x minus 1. We already wrote this here. So I'm going to send this u also into my limits of integration. I can rewrite them in terms of u. So if x is 5, u will be x minus 1. So u is 5 minus 1. If x is 1, then u is 1 minus 1. So u is going to end up going from 0 to 4. So those are my new u limits of integration. Now I can rewrite the whole integral in terms of u. So instead of going from x equals 1 to x equals 5, I'm going from u equals 0 to u equals 4. The x is getting rewritten as u plus 1. Don't forget your parentheses because it's more than one term. And then the square root of x minus 1 is u to the 1/2, which is just your square root of u, just rewriting it into something that's going to be easier to work with. And then du. Everything's in terms of u now. It has officially become a 6.4 problem, FTC. In order to use the FTC on this, we're going to have to integrate. We're going to do that by simplifying this integrand. Right now, I just need to multiply the u to the 1/2 into the parentheses to simplify. So this is going to become u to the 1/2 plus 1, which is 3/2. And then u to the 1/2 for the second term, du. Okay, so this is getting distributed into your parentheses like so. Get this expression. So now we're going to integrate and then apply the FTC. So to integrate this, I'm going to get 2/5 x to the 5/2 plus 2/3 x to the... I'm writing x's and not u's. You guys, I'm like an integrating robot here. I'm integrating with respect to u. I must keep my variable u. I know it's one of those things where I would have given you your exam back. It would have been like, why did I do that? That was a silly mistake. I just made a silly mistake, but luckily I caught it very quickly. All right, 2/5 u to the 5 halves plus 2/3 u to the 3 halves, and that expression is getting evaluated from u equals 0 to u equals 4. So I can go ahead now and just pop this in using the FTC. So I'm going to take 2/5 times 4 to the 5 halves plus 2/3 times 4 to the 3 halves minus 2/5 times 0 to the 5 halves minus 2/3 times 0 to the 3 halves. The lower limit being 0 in this case is going to zero out. That's not always the case. Don't forget, in this case, your lower limit was 0. E to the 0 is 1. So we can't just always drop off a lower limit of 0. We need to make sure that it actually is mathematically 0. But now we just need to evaluate this. Your calculator will be able to evaluate 4 to the 5 halves. If you cannot do it by hand, that is fine. So 4 to the 5 halves power. Oh, I put in 5/3. Can you believe it? Is 32. So this is going to be 2/5 times 32 plus 2/3 times 8. 4 to the 3 halves is 8. You can put that in if you weren't sure. And when you add these two together, taking 2/5 times 32, yeah, there we go, it's a little better. 2/5 times 32 plus 2/3 times 8. And your answer will be 272 over 15. So there was a lot that happened in this particular example, mostly just due to all the different little things that had to be substituted out. Not only did we have to do our standard u substitution just to rewrite the integral, but we had this additional factor of x that we had to rewrite in terms of u. And then we rewrote the limits of integration in terms of u. But everything got completely substituted. And then we evaluated this using the FTC. I feel like if I go through the method of back substituting at this point, it's actually going to look more confusing. So I might just leave this one as is. If we're going to substitute back, you would have done that here. So if you were back substituting, okay, I'll just write it in case you were like, did I do this right? For back substituting, you would have taken your integrated quantity and you would have rewritten your u in terms of x. U is x minus 1. So you'd have 2/5 times x minus 1 to the 5 halves plus 2/3 times x minus 1 to the 3 halves. And you would have taken this from your original x limit 1 up to 5. So you would evaluate this from x equals 1 to x equals 5. You still would have gotten 272/15. It's going to be the same answer. And basically this for the exact same reason. 5 and 1. 5 minus 1 is 4. 1 minus 1 is 0. Same idea. Now we're going to work a little bit with some applications here. 1, 2, 3. Okay. Sorry, the original pages are double-sided. My new pages are single-sided. And it's very confusing. All right, so here's how we might use something like this for an application problem in this section. A bottle of white wine at room temperature, 68 degrees Fahrenheit, is placed in a refrigerator at 4 p.m. Its temperature after T hours is changing at a rate of, hopefully you're like, wait, changing at a rate of ding, 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 ding. This means something. Changing at a rate of negative 18 e to the negative 0.6 t degrees Fahrenheit per hour. This means that this is your derivative with respect to time, d dt. By how many degrees will the temperature of one have dropped by 7 p.m.? And what will the temperature be at 7 p.m.? So first of all, we need to think about what's actually happening time-wise. So a couple of things to consider here. We are gonna let's first set up our integral, because you know you're gonna integrate because you were given information about the derivative, but you need to know information about the actual temperature, not the change in the temperature. So the changing at a rate of means I'm giving you a derivative. Those are keywords. And I'm trying to get to the actual function that tells me what the temperature is at a given number of hours t. I need to integrate to get back up to the original function. So f of t, we can write this however you would like. I don't know. I feel like I always like to have f as being lowercase, is the integral of f prime of t dt. So, okay, fine. But now you're thinking, like, what would my limits of integration be? Well, I need to go from a certain value of t up to another value of t. So generally speaking, I'm going from t equals a to t equals b. I just need to figure out what those times are. So let's go ahead and rewrite this integral using the information that we have. So I know that if I'm looking at t, remember that t is in hours. I'm going to be going from the initial time that the bottle was placed in the refrigerator at 4 p.m. So the initial time would be 0 hours. Like, that's when it was put in the fridge. No time has elapsed. And then at 7 p.m., that would be 3 hours that it had been sitting in the fridge. So if t is measured in hours, you're saying that t is going from 0 to 3. Okay, so those are the hours, or the number of hours that the bottle was in the refrigerator. Now I can just go ahead and put that derivative function into the integral. So it's negative 18 e to the negative 0.6 t dt. Now, this is a u substitution problem because you don't just have e to the t, you have e to the f of t. So what we're going to do is we're going to write our u substitution using the exponent for e as our function u. So we're going to say that u is negative 0.6 t, which means that du is negative 0.6 dt. Now, it is up to you if you want to try to create an 18. I probably would not. I would just say, let's just divide both sides by 0.6. So what that would look like would be negative 1 over 0.6 du equals dt. And then I'm just going to plug it into my integral directly. I think that'll be the most straightforward way of doing this. If you do not agree, go ahead and create yourself an 18. I'm not going to. So I'm going to pull the 18 out first. Well, you can leave the 18 in, I guess. It does not matter. And then we need to figure out what we're going to do about these limits of integration. Do we want to switch them? Do we want to back substitute? You know what? Let's go with back substitute on this one. I don't know. I mean, it's up to you. No, I made such a big deal about, you know what? Let's switch them. We're going to switch them. Let's say we're going from t equals 0 to t equals 3. And we know that u is negative 0.6 times t. So that means that u equals negative 0.6 times 3, which is negative 1.8. And then for 0, well, u would just be negative 0.06 times 0. So u would be 0. So again, I'm just using this u to find my my new limit of integration u with respect to Well, using these values for t that I have. All right, so now I have u limits of integration. Oh, I just realized something too. This is really actually exciting because I hadn't originally planned to do the problem this way, but look at how my upper limit of integration now is smaller than my lower limit. I'm really excited. I get to use my favorite property. This worked out beautifully. Okay, it's fine. I know. So I'm sorry. I get really excited about things like this. All right, so instead of going from 0 to 3, remember, this is kind of why I write these in the same order as I see them, because a lot of times we want to write the lower limit or the smaller number as the lower limit. It isn't always the case. In this case, 3 corresponded to negative 1.8. And then 0 corresponded to 0 still. So nothing too crazy there. Okay, so I still have a negative 18 inside the integral. I have e to the u, and then my dt was negative 1 divided by 0.6 du. Okay, so everything is now accounted for. Everything is written in terms of u. I'm just going to simplify and integrate and then apply the FTC because I already have u limits of integration. I don't have to do any back substituting. Oh, so you know what? Oh, I was going to use my special property, but now I realize that these two together are going to multiply to give me a positive value. We can still use the property. We'll find a way. Okay, so what I'm going to do to simplify this is I'm going to take 18 and divide it by 0.06, and I'm going to get 300, or not 0.06, 0.6, sorry, it was 0.6, 30, not 330. Okay, so now I have u goes from 0 to negative 1.8. I'm going to have 30, and then e to the u du. Okay, so everything, again, make sure everything's accounted for. The negative times the negative gives you a positive. All that leaves you with is e to the u du. And now what I'm going to do is, I was waiting to use my favorite property. We're going to use it now. This is going to be, watch. It doesn't, you don't have to use the property. I just like to use the property. I want to take the lower value, the smaller value, and make it the lower limit of integration. In order to do that, I'm going to go back and use this property that says I can just multiply it by negative and switch the limits of integration. Again, you don't have to. I just want to see, I want to show you how you would use this practically in a problem. So I'm going to say this is negative 30 times the integral from negative 1.8 to 0. And then e to the u du. Okay, I know. I made it seem like I was doing something so cool, and maybe you're like, really? That's what she was excited about. Sorry. I thought it was nice. I don't know. Whatever. E to the u. The integral of e to the u du is e to the u. And then we're going to take that from negative 1.8 to 0. So now I can just go ahead and insert these directly into my expression. So this is going to be negative 30 times e to the 0 minus e to the negative 1.8. And e to the 0 is 1. And then we're going to have to just like come up with a number here, which is fine. So let's go ahead and just evaluate this. If I had just asked you to find the integral, then this would have been fine. But this is an application problem. And for application problems, a lot of times we need to be able to approximate this so the answer means something. By the way, if you've forgotten what we're doing by now, we're trying to find out for the original function what the change in temperature was over the hours t equals 0 to t equals 3. So over the 3 hours that it was in the fridge, we're trying to figure out like what was the temperature change, taking us from the rate of change back up to what the actual temperature change was. All right, so I'm going to approximate this. Negative 30 times 1 minus e to the negative 1.8, and you negative 25.04-ish. Okay, now let's talk about units here. You were given a rate of change of temperature in degrees per hour. Your rate of change was per unit time. When we went back up from the derivative to the original function, we're just going back now to degrees, not degrees per unit time. So our temperature changed by negative 25.04 degrees. So this was a drop in temperature over 3 hours. So if having the negative answer seemed wrong to you, remember, you put a bottle of wine in the fridge and then, oh yes, you put a bottle of wine in the fridge. It was at room temperature. And of course, it's going to get colder while it's sitting in the fridge. So if the temperature dropped, it's because it was sitting in the fridge for 3 hours. So it dropped by 25 degrees. So negative just means the temp went down by that many degrees. You wouldn't expect it to go up. So if negative bothered you, you'd be like, wait, it was a drop in temp, it went in the fridge. This is not a case where like you took the bottle out of the fridge and put it on the counter. That is a case where you'd expect the temp to go up. But you took the room temperature bottle, you put it in the fridge, the temp goes down. All right, so that's the change in temperature. So that means, let's see, by how many degrees would the temperature have dropped? So this is part of your answer. And then the other part is, what will the temperature be at 7 p.m.? So at 7 p.m., you're going to take the initial temperature of the bottle, which was 68 degrees, and then take off the amount that it dropped. And then this gets you to about 42.96 degrees Fahrenheit, technically, but degrees is enough as far as the unit is concerned. Okay, so that answer both of those questions. Now, what's kind of cool about this section is you have some application problems that you could actually do using methods that you learned in 6.1 for initial value problems. So I'm going to show you one other way that you could have looked at this problem. Well, we knew we had a derivative that we were given in the original problem. So let's say we did not turn this into a definite integral. And let's say that we instead just said, okay, well, it must be the case. Let's see, we integrated this and we got negative 30 e to the negative 0.6 t. That would have been our function. Alternatively, we could have said that f of t, oh, why am I using capital F? I used lowercase f, so I need to be consistent with that. When we integrated, that's essentially what we were finding. It's just that we happened to apply these upper and lower limits of integration. So we would say this was negative 30 e to the u, which was negative 30. I know, you're like, f of t, where's this u coming from? Just sub it back in. U is a negative 0.6 t. Okay. So let's say that instead of using a definite integral, you integrated, you found this, and then you said, okay, we've got that plus c. So using methods from 6.1, or technically 6.2. Okay, have you done that? You could then said, all right, I have an initial condition. So we can solve for c using the initial condition. And the initial condition was that at t equals 0, f of t, the temperature was 68 degrees. So you could have used that and said that f of 0 was 68. Now, if you did that, and you could pop this back in and say, okay, well, if f of 0 is 68, Well, that means that negative 30 e to the 0 plus c is 68. And then you could solve for c and say that c must in this case be 38 because e to the 0 is 1. So c is 68. Why don't I have this as negative 30? Oh, you know why? Oh no. It's because I used my special property and switched the limits. Guys, I've got myself into a pickle now. Yeah. Okay. This shouldn't be negative. It should be positive. Oh, I've got myself into a pickle. Okay. Let's say you're back here, right? 30 e to the u du. See how I switched my limits and made it negative? That was something arbitrary. I only did that just to switch these limits of integration. So really this should have been positive if I was leaving it as an indefinite integral. And that means that c is 68 minus 30, and c is 38. Oh, I botched it. Listen, I do what I can. So your original function is then going to be 30 e to the negative 0.6t plus 38. And then you're just going to evaluate this at 3. F of 3 is going to be approximately 42.96 degrees Fahrenheit when you put it into your calculator. So that would be another way of doing this problem. So that also means that there are other application problems that you looked at in 6.1 and 6.2 that you wouldn't have known to use a definite integral for, but now you do know how to use a definite integral. So there are going to be 2 ways of doing these problems. All right. So that's an application problem that illustrates how you would use definite integrals with substitution to find specific values, like given rates of change, how to talk about actual changes in your quantity. The last thing we're going to talk about today is average value. Okay, so this goes here, sorry. Average value. Blah, blah, blah. Okay. We didn't talk about all these sums, but I did talk to you kind of about where the definite integral comes from. We looked at all the little curves with the rectangles. If you don't want to look at this, fine. I'm going to give you basically an overview of this. It's pretty easy to use. So the formula for average value is 1 over b minus a times the integral from a to b of f of x dx. It's just finding an integral from a to b, but then multiplying by 1 over the length of this interval from a to b. Now, the idea behind average value is basically you're trying to find the average height. So this picture kind of illustrates that. So what you're really doing here is you're trying to figure out where you would have to basically cut off this horizontal. So where would you cut through here horizontally such that the area under a curve is the exact same as the area of this rectangle? So that's what this horizontal line is representing. So if you can imagine taking this shaded portion that's above the horizontal line and then sort of spinning it 180 degrees and fitting it into this little section, then you'll be able to see that the areas were exactly the same because the piece that's missing is the exact same area as the piece up here that was shaded, not included. So the average value is just the average height, and you're just assuming that the rectangle has the same area as the shaded region under the curve. So when you think about average value, you think about height. B minus A that's just the length or the width of your rectangle. And then you're multiplying that by this integral. We know that the integral represents the area. Well, the area of a rectangle is just the width times the height, or the base times the height. So we can rewrite this by just multiplying both sides by width, and area is width times height. That's where this comes from. I'm not too worried about you being able to really show a whole lot about this, but I do want you to be able to use the formula for average value and just to find average value. So whether or not you have like a complete hold on this, I mean, of course, I would love for everybody to understand how this average value works. As long as you know the formula and you can use it, I'm pretty thrilled at this point in the semester. I know we're wrapping things up here, but basically that's just what this means. You're trying to find where vertically you would put a horizontal line through the function such that you create a rectangle that has the same area as the area under the curve. That's the idea. All right, so let's do a problem. The average value we're going to look for here is we're going to find the average value of f of x equals x squared over the closed interval from -3 to 1. So what I'm going to be doing here is, remember, when you're given average value, we're given values for A and B. A is always going to be that left-hand endpoint, and B will be the right-hand endpoint. So if I'm talking about B minus A, B minus A is 1 minus -3, which is 1 plus 3, which is 4. So all we're going to do in this case is set up an integral where we're taking 1 over B minus A, so 1/4, times the integral from A to B, so from -3 to 1 of x squared dx. And then I think we should look at this in our calculators too, and we're done. Of course we should. But right now, let's just integrate. All right, so this is just 1 over B minus A, your 1/4. And then you're just multiplying by the integral from A to B of f of x dx. So we have 1/4 times 1/3 x cubed, and we're going to take that from -3 to 1. And this is 1/12 times 1 cubed minus -3 cubed. Which is 1 minus, and then -3 cubed is -27, minus the negative is plus. You'll get 28/12. 4 goes into both of those, so you'll get 7/3 as your average value. So that means that if you cut off your height at 7/3, you should be able to create a region. You should be able to create a rectangle such that the area of the rectangle is the same exact area as the area under a curve. So let's look at that in our calculators. So we're talking about x squared. So I'm going to go to my y equals, and I'm going to just enter x squared. Hopefully this graph is very familiar to us. And I'm only really going to look at this on the window from -3 to 1. So maybe I'm just going to go from -3 to 1 on my graph. I know that if I'm talking about x squared, I'm talking about values. I'm just taking my x and squaring them. So yeah, I guess my y max is good. If I'm going from -3 to 1, I'm only squaring values, so they're only going to be positive. We don't really need this y min to be -10. We just set this to be equal to 0, and we should be good to go. All right, ready? Okay, so I'm going to graph the graph. Okay, so that's y equals x squared. If you would like, let's see if we can calculate the area number 7 from -3. Oops. Okay, I'm going to have to do this over again. Okay, so I can calculate number 7, -3, 1. Okay, so this gives us our whole area. And notice that this is 9.3, so 9 1/3. 9 1/3 is 27, 28 thirds. But if you take 28/3 and multiply it by 1/4, you get 28/12, which is the average value that we found. So that's good. So the area portion itself was like 9.3. When you multiply it by 1/4, you get 28/12. What I'm going to do now is pop in this function 7/3 for the height. And we should be able to see this line where we've created a rectangle from -3 to 1 such that the area under the curve would have been the same exact area as the area of the rectangle. So if the rectangle has an average value of 7/3, that means you're taking 7/3, which is the height, times the base of the triangle, which is 4, and you are getting the area. So this is the base, height times the base is the area of the rectangle. Okay, so you'll find that the area of the rectangle in this case is 28/3, which is 9 1/3, which is the exact area that we found when we computed our area using Calculate 7. So what the idea is here is that this rectangle is getting cut off here at 7/3, which is 2 1/3. I could take all of this portion under the curve that's on top of the rectangle, and if I could redistribute it, it would fit exactly into this blank space underneath this horizontal line where there is no area. And that means that this area above the horizontal line is the exact same as the area that's blank underneath the horizontal line. I know it's a weird thing, but it's really cool. I really like average value. So I don't know. It's cool because I mean, you can kind of visualize it. So if you would have gotten a line that was like way up here, you'd be like, wait, that doesn't look right because there's only a small amount of area. It has to cover this giant space. But this makes sense. Like imagine if this was just filled with sand, you'd be able to like spill it over here and exactly fill the rectangle. So it's pretty cool. You know, my opinion of what's cool just doesn't always match up with what you all think is cool. I'm sorry. So that's average value. We have one more problem to do, and then we're out of here. The sales of universal, there we go, instruments in the first t years of its operation are approximated by the function s of t equals t times the square root of 0.2 t squared plus 4, where s of t is measured in millions of dollars. That's important. What were Universal's average yearly sales over its first 5 years? All right, so if we're talking about the first 5 years, we're talking about t equals 0 to t equals 5. So that means we're going to be setting up an integral from 0 to 5, and we're going to be dividing it by b minus a. So that means I'm looking at, if you want to think about this as being a closed interval, if you find that to be helpful, that is fine. Again, this would be a to b, and then b minus a is 5 minus 0, which is 5. Okay, so we're talking about average yearly sales. That's where we're going to be using this average value. We're going to be taking our integral, and we're going to be just multiplying it by 1 over b minus a. All right, so let's go ahead. 1 over 5. This is your 1 over b minus a. And then we're going to multiply that by the integral from 0 to 5 of t times the square root of 0.2 t squared plus 4 dt. All right. It's a substitution problem. I'm going to change my limits of integration because that's what I want to do. And we're on the last problem, so I feel like I should get to do what I want to do. Okay. U equals 0.2 t squared plus 4. Hopefully we're noticing this is a composite function, and u is just going to be the radicand of the radical. du is going to be twice 0.2, which is 0.4. And then drop your exponent by 1 dt. I do not have a 0.4. I'm just going to go ahead and divide it out. If I divide both sides by 0.4, really you're just taking 1 and you're dividing it by 0.4, which is 2.5. So 1 divided by 0.4 du is t dt. That means 2.5 du is t dt. That's where that comes from. All right, so let's match it all up. tt is 2.5 du. Then the radical itself is just going to be the square root of u. So let's go ahead and make some substitutions. Oh, and let's change our limits of integration as promised. I have t going from 0 to 5. U is going to be whatever t is squared times 2 plus 4. So to enter this, I'm going to say 0.2 times t squared plus 4. And I get u equals, here, I'll just write it out too, so it's there. 9. And then when I do this again, 0.2 times, when you probably don't have to put in your calculator, but why not? 0.2 times 0 squared plus 4 is 4. So now I'm going from u equals 4, u equals 9, and I'm going to rewrite the whole integral in terms of u. So I'm going to go ahead now and say 1/5, because it's a constant, it's going to stay. I'm going from u equals 4 to u equals 9 of 2.5 times u to the 1/2 du. And then you're going to take your 2.5 and divide it by 5 and write that as a half. So we have 1/2 and then times 2/3 u to the 3/2 when we integrate. And that's going from u equals 4 to u equals 9. If you opted to back substitute and you didn't change your limits, this is where you go back, substitute the u expression for x, or for t in this case, and then just use the original limits. But I already changed my limits, so I'm just going to use the FTC with these limits. So I have 1/3 times 9 to the 3/2 minus 4 to the 3/2. Let's see, 9 to the 3/2 is, I think, 27. Yes. Minus 8. 27 minus 8 is 19. Now, this is an application problem. We've talked so much about, like, yes, I always want your answers to be exact, but in an application problem, we want to be able to somehow use some sort of context with it. So 3 goes into 19 6 times with 1 left over. So this is approximately 6 1/3. Now we need, or it's exactly 6 1/3, I should say. We should approximate it a little bit differently. We also need a unit. So I can say that 6 1/3 is approximately 6.33. And then my unit here is millions of dollars. So I'm going to go ahead and say that the average yearly sales were in millions of dollars after or over its first 5 years of operation. Okay. Let's write this on the next line. I'm running out of space here. We're going to say it's about $6.33 million. And you can leave that like this. I mean, officially we'd have to go 6,333,333.33, and that's crazy. So I would leave my answer like this, and the dollar sign's on there, so you don't need to repeat that. Just don't say $6.33. Don't do that. It's a millions. And that would be weird too. Like, really, average yearly sales $6, really? What kind of sham company is this? And that's it. All right. Like I said, I'm not going to require you to use one method over the other, but I really strongly recommend that you switch your limits to U limits, and then you don't back substitute. You're not going to do both. You can do one or the other. So either change your limits or back substitute. Don't do both. Don't do both. Resist the temptation. Students have to resist the temptation to overdo it. All right. That is all that I have for you today. I hope you have a wonderful rest of your day. We only have 2 sections left in the chapter, 6.6 and 6.7. Next time we'll talk about finding the areas between curves. And then after that, we'll just talk about some more applications and we'll be done with the chapter. Have a wonderful rest of your day. I'll see you next time.